Today we're going to go over the stress tensor for a fluid. This is going to be a little heavy on the tensor math. It's not really critical to the other topics we'll be going through this semester. Well, in a few places we might touch on it, but I wanted to go through the derivation in detail here, just so it doesn't seem so magical. I think sometimes if you just look at what the stress tensor is, it just looks like it comes out of nowhere. So let me relate first to what you have seen in a beginning fluids class. You'll have seen something like this, right? That the stress, shear stress, is linearly related to, say, a velocity gradient, du dy, right? So this is stress. This is a strain, or really a strain rate. And this is the proportionality constant called the viscosity, the dynamic viscosity. And so we have a linear relationship here, characteristic of a Newtonian fluid. This really, though, only applies in one dimension. And in a three-dimensional flow, there are actually 9 components, 6 unique components of the stress tensor, right? Because this has, as we discussed, 2 components, a direction and a face. And the strain tensor also has 9 components, 6 of which are unique, right? Which is du dx, du dy, du dz, dv dx, dv dy, dv dz, dw dx, dw dy, dw dz. So let's discuss kind of this generalization and what happens in this 3D case if we still have just one term or not, and what this looks like. So first, let's start with the strain. Strain tensor, again, it's really a strain rate tensor. And so what we have here is dui dxj, right? So those are those 9 components I just talked about. There's the 3 different components of u and 3 different components of j. So I'm going to be doing everything in terms of tensors. Again, if you are uncomfortable with that, you could think of this as a matrix. We could certainly represent it in a matrix form. Sometimes that is a convenient thing. Okay, so the strain tensor, what I'm going to do is I'm going to rewrite it. I'm going to expand it into some additional terms. And this is going to look weird at first, but I'm just going to do it. So I'm going to say it's 1/2 times dui dxj. I'm going to put 2 terms here, another half. So basically, so far, all I've done is I've taken that same term and I've split it into 2 parts, right? This is exactly what's over here. This is exactly what's over here. So I just put a half over front of each of them so that I recover back my original function. And then I'm going to add, notice I'm going to switch the index here, j, I. And then on this side, I'm going to subtract j, I. So this term and these terms cancel, and then this term and this term are the same. They both have a half, so they add up. They give me my original strain tensor. Now, that seems a really strange thing to do, right? Why did I just make the simple thing really complicated? But what I did is I broke up my original tensor into a symmetric component and an antisymmetric component. So this component here is symmetric. We call this the strain tensor, right? Whereas the original one, I don't know if I actually called it the strain tensor. If I did, I shouldn't have. It's just the velocity gradients. This is what we call the strain tensor, the strain rate tensor. It is symmetric, and symmetric means, right, that I could switch the order here. Okay. The other component here is called the vorticity tensor, and it is antisymmetric. Okay. Antisymmetric means that if I switch the indices, I get a negative sign. Turns out any second order tensor, again, you can think of that as a matrix, I can always split it up into a symmetric part and an antisymmetric part, or I should say the sum of a symmetric and an antisymmetric tensor. So the reason why we do this, and in this case, they have special names, in general, if I had just some general tensor, they may not have a specific name. But the reason why I do this is that this is vorticity. Vorticity, if you remember, or the reason why I call it the vorticity is these components are the vorticity components. And recall that vorticity is the curl of the velocity. It's also twice the angular velocity. So in other words, it's associated with rotation. This term here is purely rotation of the fluid. This term here is purely deformation. So if you think about a strain, right, I think about our 2D picture of strain. I got some box and I put a strain on it. Depending on how the strain is, it could rotate the box or it could deform, right? I could get something that's rotating or I get something that's kind of stretching and straining, right? So this term here, the strain rate tensor, is all deformation, and this term here is pure rotation. So the reason why I wanted to do that is that rotation does not create a stress. Just like a pure translation does not create stresses, pure rotation does not create stresses either. But this shear strain definitely does cause stresses. So we're going to relate our stresses to strain, just like we kind of did in 1D, right? But we should only relate this component here, the symmetric component of my velocity gradients, or in other words, the strain tensor. Okay, so what we could do, so we're going to forget about this one for now. This is the only thing that's going to matter when we relate to stress. And if I was to write this in a tensor notation in the most general way possible, right, I've got my strain tensor. It has two components. Sorry, stress tensor. And I have my strain tensor. It also has two components, which are just different indices here. And a Newtonian fluid means that there's a linear relationship between these two things. That's an assumption. And most fluids are actually quite well represented as linear, including air. But things that are, there are fluids that behave in a nonlinear way, I would say the non-Newtonian fluid. Some things like blood, honey, paint, ketchup, things like that, that are, they behave in a non-Newtonian behavior. But in the most general case, I've got some fourth order tensor here that maps, right? This is a sum over K and L, right? A double sum. I sum all these things up across all of these different constants, and I get my stress tensor. And in the general case, to map one second order tensor to another second order tensor, there's 3 components for each of these. So 3 to the 4th power, that's 81 potential constants to relate these. Fortunately, we won't have nearly so many because a fluid is isotropic. And isotropic means that no matter what direction orientation I choose, right? So for some coordinate system, that my fluid properties have to be the same, right? I'm going to get the same pressure, same density, and so on. So because of that behavior, actually the most general, this part comes from tensor theory. I'm not going to derive it, it's a bit lengthy, but the most general isotropic 4th order tensor is as follows. Lambda, which is some constant, delta ij, this is the Kronecker deltas that we've seen before, mu delta ik, delta jl, plus nu delta il, delta jk. And again, like I said at the beginning, just as a warning, this is a little more, this is pretty advanced on kind of the tensor math. So, you know, if you don't follow everything, it's not a big deal. But, you know, I did want to put this out there so you could see that this is just not, you know, kind of where this comes from. So again, if you remember the Kronecker delta, those of you that done tensor stuff, you've seen this before, right? It equals 1 for when I equals j and 0 otherwise. So you could also think of it, if you like matrix representations, kind of like a diagonal matrix, but that's a little bit too, it's not quite the same, right? Because we got kind of these different indices. So this is the most possible general isotropic. So I should say this here is isotropic 4th order tensor. So in other words, I don't have 81 constants anymore. I have 3, lambda, mu, and nu, that are going to relate my strains to my stresses. Now, I have one other condition I can apply. I know that my stress tensor is symmetric. I know that tau here is symmetric. So in other words, if I switch the indices, tau ji equals tau ij. So that also means that if I switch them on k, right, if I switch this, then I should get the same, this expression is going to be equal. So let me just switch all the J's with the I's. This is a J, K, I, L, J, L, I, K. So that means that this whole term has to equal this whole term because this is still the same. And we just said tau ij equals tau ji, and this is the tau ji term. So this whole expression equals this. This is the same as this one. And this is the same as this. Notice the indices are flipped, but that doesn't change anything, right? This is a symmetric tensor. So tau or delta ij is equal to delta ji. So these two here are equal. And notice that this here is equal to this, right? There's a JK, JK, IL, IL. So those two are equal. And then notice that this IK, JL, and here I've got IK and JL, that these two are equal. So in other words, for these two expressions to be equal, then mu and nu, right, have to be equal to each other. So if I have a symmetric isotropic tensor, I'm only going to have two constants, just mu and nu, the most general case. So I could write it like this: ijkl equals lambda delta ij delta kl plus mu. And since this is mu and nu, this is also now mu, then I'm just going to factor that out and add these two terms together. I get ik jl plus il jk. Okay, so this is now the most general symmetric isotropic tensor I could have, and I don't have 81 constants. I have two constants, mu and lambda. And even though that was kind of a pain, the analogy, that you have seen something like this before, not the math, but the concept is in a structures class. If you have an isotropic material, recall that we can define that material with just two constants. Typically we'd use the modulus, what we call the modulus of elasticity, and Poisson's ratio. You may also recall that there's a shear modulus, but it's just a function of the other two. So there's only two unique constants. So you could say E and G, or E and nu, or nu and G, any two, right? But there's only two constants to fully define an isotropic material. Same thing here, two constants. Because it's isotropic, I should say isotropic and symmetric, which is also true for the stress tensor and structures. Okay, so I did all this crazy stuff. So what I'm going to do now is I'm going to take this expression here and plug it in. Okay, so I get now an equation for my stress tensor. So let me write that out. It's going to be a big, ugly thing. Tau ij equals, I'm going to kind of distribute it too. Let's see, it's I'm going to multiply this term. I'm going to multiply it through on each term. So I'm just going to expand everything out. So let's see, it's going to be lambda delta ij delta kl times epsilon kl plus mu times delta ik delta jl epsilon kl plus delta il delta jk epsilon kl. Okay, so again, all I did is I took this expression here, plugged it in, and I took the epsilon, I just multiplied it through. So I put 1 on each of these three terms here. All right, so one of the properties of the Kronecker delta that you need to know is contraction, and it looks like this. If I have any index, and I'm just drawing this as a vector, but it could be any order tensor, it doesn't matter, and I multiply by delta ij, then you could think of that these i's are going to disappear, and I'm just going to be left with the j. This equals aj, okay? And you could see that like this. I could write it out explicitly. Remember that this double I here means a sum. So this is equal to A1 times delta 1j plus A2 times delta 2j plus A3 times delta 3j, right? And so I have to pick the j that I want. And let's say I choose j equals 2. So if I pick the j equals 2th equation here, right? Notice that this will be 0, because remember, delta ij, it's always 0 unless the two terms are equal. So this is 0 and this is 0. The only term that gets left, this is 2, 2, so this is a 1. The only term that's left is a2. So in other words, this thing always contracts and I'm left with the component, the free component, j in this case, right? So I'm going to apply that rule here to simplify this stuff down. So I'm going to have lambda, and I've got an L and L, so I can contract that. So let's see, I'm left with this delta ij. This will become an epsilon, say kk, or it could be LL. You could write it either way, it doesn't matter. It's just a dummy summing index. You know, it can be any letter, that doesn't really matter. And then here I've got this L's are gonna cancel, if you will, and leave me with a J there. And these K's will cancel, putting the I in. And so I'm left with epsilon I, J. And then in this case, the K's contract and I get a J in the first index there. And then these L's contract and I get an I, okay? Again, if you haven't done tensor math before, this is gonna look really weird and you don't have to really worry about it. This is just really optional material here. These two are equal because it's symmetric. The strain tensor, remember, was a symmetric thing. So epsilon ij equals epsilon ji. So I get lambda, I'm gonna write it in the opposite order here. Epsilon k delta ij plus 2 mu epsilon ij. Okay, and yeah, that's it. But I'm going to write out my strain tensor because remember what it looks like. It's this thing. I'm going to now plug that in. Remember, there's a 1/2, and it's dui dxj plus duj dxi. So if I plug that in, I get, and I'm going to write this term first. I get the 2. So I'm going to pull out the mu. The 2 cancels with the 1/2, and so I get dui dxj plus duj dxi. And then the second term, I've got lambda, and I've got this delta ij. But what is epsilon kk? So that's a repeated index, so I'm going to sum. So that means I've got to have a, let me just write it out here. Let's see, I've got a, well, I'll just write it like this, right? It was a 1/2. I'm going to write in different colors. So it's epsilon kk. It's going to be 1/2 duk dxk plus duk dxk. So those are the same thing. So I add them, and the 2 cancels with the 1/2. So I just could write that as duk dxk. That's the divergence, right? That's just a sum of my velocity components, right? So du dx plus dv dy plus dw dz, that's the divergence. Okay, so that's my expression. This is the strain tensor, although we're not quite done because we have a problem, which is I have 2 unknowns, 2 parameters here that I need, just like we had before. And this is called the first coefficient of viscosity. And this one is called the second coefficient of viscosity. We've seen this one for sure. It's the same one that we did in 1D. This one we may or may not have seen, but it's called the second coefficient of viscosity. And the problem is we don't have a model for it, so we need some way to deal with this. Okay, and the way we're going to deal with it is something called Stokes' hypothesis, and I want to kind of motivate it in more of a physical way. So we're going to have to do a little bit more math to do that. And so here's what we're going to do. We're going to take this stress tensor that we have now, and we're going to separate it again into 2 terms. Before we separate into symmetric and antisymmetric, you can always do that. Another way we can separate things into what's called a hydrostatic component and a deviatoric component. So we're going to do that. And I can explain maybe first what this would look like. Let's say I had, maybe I'll just do it as a picture. Okay. Let's say I had stress tensor, and it's got a component in this direction that's 3, a direction that's 2, and one that is, just to keep things simple for me, let's say this is 4. And then I'm only going to put one component on the sides here. Let's just do this one, and we'll call it, and it's on this back side and this side, right? We'll call that, I don't know, 1. Okay. So if I was to write this as a matrix, if we're more comfortable with that, we could say tau is, and we'll just call this, we'll call this X, Y, and Z. Okay. So that would be X, Y, and Z would be the diagonal components. And then this one would be, I guess the way I've drawn it, this would be like my YZ component. So that would be, this one would be a 1. It's symmetric. So this is a 1. And then I just will say the others are 0, right? I said there's no shear stress on this face and no shear stress going this way, right? Or going this way. So those other ones are 0. So let's say this is my stress component. I can always divide it into, again, what's called a hydrostatic component and a deviatoric component. The hydrostatic component, the way I figure that out is I take the diagonals here and I average them. And that gives me the, and I put that along the diagonal, that gives me the hydrostatic component. So in this case, the hydrostatic component would be the average of 3, 2, and 4 is just 3. So it'd just be 3, 3, 3. It's always a constant times an identity matrix, okay? And the reason why it's hydrostatic, it's just like a hydrostatic in fluids, it's just like a pressure. It behaves like a pressure, meaning it's the same for every direction. It's hydrostatic, so the orientation doesn't matter because it's just a scalar times an identity, right? So it doesn't matter about the orientation. And the deviatoric is everything that's left over. So in other words, I take this complicated, whatever it is, and I say it's equal to something that is just equally loaded in all directions, plus whatever remains, which in this case is like a -1 this way, right? It's a 1 going in, it's a 1 coming out here, and it's this 1 on the shear, whatever. Okay, so to write that out, and the math here, the deviatoric component here is just 0, -1, 1, 0, 0, 1. It's just a coincidence these all are 1s. There's nothing special about 1. It's just that this tensor here, oh, sorry, you can't see that. It's not showing for some reason. Anyway, I don't know why my laser thing isn't working, but this tensor here is equal to this plus this, okay? So, just stopped working. Oh, it is working. It's just not working on my screen. All right. So again, this looks strange, but you may have seen this too in a structures class. If you ever looked at von Mises stress, this is exactly the way it's derived, is that you take out the hydrostatic component and what's left is called the, they call it distortional energy in that case. And that's what's assumed to cause failure, is the distortion from the sort of mean stress, right? So in other words, this is like same kind of thing in stress. This is what maybe stretches or compresses it equally in all directions, just like a hydrostatic pressure does. It's going to be equal everywhere. And then the deviatoric is any deviations from that. Okay, so that was just a motivation for how we would do that. Oops. So in our case, yeah, I guess I'll just go through the math here. Might as well. Yeah, let me do that. In our case, the hydrostatic component, if we were to write it in tensor notation, it's the average of the diagonal components. And to get the diagonal components, I just sum across the diagonal. So I put a sum. So they have this diagonal because they have the same thing. And it's times an identity matrix, which in the tensor notation is going to be the Kronecker delta, right? So this is my hydrostatic component of the stress tensor. If I go back and look at what tau is, it's this thing. So if I do the tau kk thing here and I sum it, I'm going to kind of do it kind of quickly here. What I get is 2 times mu times duk dxk plus 3 times lambda times d uk dxk delta ij. And so if I simplify, what I get here is I get 2/3 times mu plus lambda times my divergence times the identity here. And this new quantity here, we call this the bulk viscosity, and that's a kappa, okay? Bulk viscosity. All right, and what's left is the deviatoric component. So delta ij is equal to my original stress tensor minus the hydrostatic component, and that just becomes mu dui dxj plus duj dxi minus 2/3 mu duk dxk delta ij. Okay. So that's what I have. I got these two components, and Stokes' hypothesis, write that down. Stokes' hypothesis was that kappa is equal to 0. In other words, that this term is gone. Okay, and so all I'm left with then is the deviatoric component. It turns out that it's hard to measure kappa. There have been some measurements and have shown that, yes, in many cases it does seem to be negligible. There's some theory to support that, but there's also other measurements that have shown it to be quite significant. And maybe more recent studies suggest that actually maybe it's not kappa that's negligible that we should say, but it's rather this product, kappa times the divergence is negligible. In other case, we get the same conclusion, which is this, that the hydrostatic component does not contribute to my stress. It's negligible compared to this component. And, to physically motivate that, we could say, it kind of makes sense, which is, I guess another way to say it is that my thermodynamic pressure, the pressure thing that we normally talk about as pressure, this thermodynamic pressure, is the same as a mechanical pressure, meaning that my shear stresses don't add a pressure-like term. Remember, this hydrostatic is a pressure-like term, meaning it's equal in all directions. So the shear doesn't cause this equal expansion or equal compression like regular pressure does. It doesn't behave that way. The only thing it does is distortions about, that kind of equal compression or tension. So it doesn't behave like a pressure. And that seems to make some sense, right? That would be the role of shear is kind of a deviation, not an actual sort of pressure term. The other way to think about it is that we call this, if this existed, that the thermodynamic pressure plus this is a mechanical pressure, and we're saying that those two things are equal because this is 0. And another way to think of that is that just that we reach thermodynamic equilibrium pretty quickly. So, okay, so if H is 0, right, if this is 0, that means that my shear stress is equal to the deviatoric component. So this expression here is my stress tensor, tau ij, okay? And you notice if we relate it to what we had before, say just like du dy in 1D, it looks kind of similar. So I'm going to write tau over here, right? Because this is tau. It looks kind of similar, right? This first term, but of course now it's expanded into 3 dimensions. So for example, the tau xy component would be mu times, say, du dy, that would still exist, but I'd also have plus dv dx, right? And potentially I'd have this term. This term is in many cases 0. If it's incompressible, remember this is the divergence of the velocity field, and that's 0 for an incompressible fluid. For incompressible fluids, this is 0. In a boundary layer, you can show that these shear stresses are way, way bigger than any of these normal stresses. This is also negligible. So really, it's only for viscous compressible fluids outside of the boundary layers that this becomes a term that's maybe important, but it's, again, often smaller. So it's not too different from what we have, but it is more complicated. Okay, So that's it again. This was kind of a deep dive. Consider this an optional section. If it didn't really make sense, don't worry about that. I think maybe one of the key insights though is kind of the relation that there's a relationship between stress and strain, that there are two, in general, two unknowns, just like there would be for a structure, two constants to define the material in this case, or to define the fluid. And in this case, we don't have a second term, or we don't have a way to model that. And so we take this hypothesis that for a fluid, shear stress doesn't have a pressure-like component, just only a deviatoric component. And in that case, we get rid of that second term, or at least we have a way to model it. Actually, it becomes this 2/3 lambda, right? Because if kappa is 0, that means lambda is equal to minus 2/3 mu, which is exactly this. So we have a relationship between the two. And that, yeah, and so then the only unknown that we need is the viscosity. So this is the shear stress term. If you assume incompressibility and you go and plug this in, then some things simplify, right? For one, this term goes away. And if you remember the Navier-Stokes equation, it's actually derivatives of this term that appear. And for the incompressible case, if I expand this out, I get additional terms that are divergence terms and will cancel. And the incompressible Navier-Stokes equations are actually quite a lot simpler. They don't have this kind of long, messy shear stress expression. It's just a Laplacian velocity vector. But you can go look in the book if you're interested to see that. I think that's enough for today. Stress tensor.